Okay, so what function did they suggest here on page 138? I'm talking about the permutations on the bottom page 138. You're looking at one example earlier. Yeah. And so we have to first of all define f. So it says for each Ri, and Ri is going to be a rotation or one of the permutations in D4. So for each Ri in D4, we're going to define f of Ri to be what? The permutation that does what? Of the diagonals produced by Ri. So let's think about this for a minute. Suppose we had our square, and in the book they have this diagonal and they label it 1, and they have this diagonal and they label it 2. So if we think about just, here's A, B, C, D. If we do a rotation, say, of 90 degrees, then that is going to take A to what value? B. B goes to, C goes to, and D goes to A. Now, when you think about that, that has put the diagonal where? Where has diagonal 1 gone to? Diagonal 1 goes to diagonal 2. Now, suppose we looked at 180 degrees, the rotation through 180 degrees. A now goes to C, B goes to D, and C goes to what? And D goes to B. The first diagonal went to the second and then went back to what? 1. So diagonal 1 goes to diagonal 1. Diagonal 2 goes to diagonal 2. So the first one interchanges diagonal 1 and 2, the second one leaves them the same. That's the only two options that we have for our permutations. It either goes to it interchanges the diagonals or leaves them the same. So it says define f of Ri to be the permutation of the diagonals produced by Ri. What is it doing? Is it taking diagonal 1 to diagonal 2, or is it leaving them the same? Let's define the permutations of the diagonals to be. And they give this in the book. That was good. So diagonal 1, diagonal 2. The diagonal 1 could go to 1 and diagonal 2 could go to diagonal 2. Or the other option is 1 goes to 2 and 2 goes to 1. Those are the permutations on the diagonals. That makes sense? So either f of Ri is going to be the first one, or f of Ri is going to be the second one of those permutations. Now we just have to verify that this is a homomorphism, so we have to verify the property on the homomorphism. So we have to get two elements in D4, and then we have to think about what's happening to those two elements. What happens when we just operate on them? So if we were looking at Ri composed of Rj, because this is function composition here. What happens when we do the function composition of the two objects? It's going to be another permutation, right? Because this is a group. So the function permutation is another permutation. So we just have to verify that in the case of Ri followed by, well, Rj followed by Ri, that that has the same behavior on the diagonals as if we just looked at the permutations of the diagonals. Does that make sense? So that means we actually have to look at the table of the symmetries of the square of D4. You guys remember where that is in the book? There's a whole table of those. Oh, I don't remember what page number that's on. I know the S4 was on 70 something, so let's go look there and see. 73? Yeah. So we have, they give us R1, R2, R3, R4, and if you, oh, they don't give us a multiplication table for it. There are 6 of them. So if we were actually verifying this, we would write down the multiplication table for each of them. So let's do that. I think we've done the multiplication table for this. Before we do that, let's put our multiplication table over here. So we need, let's see, 2, 4, 5, 6. So I need 7 rows by 7 columns. And then this is just our function comp. How many were there? 1, 2, 3. Yep, there's 8. It goes to 7. I saw it as 6. So that means we need, oh, I didn't want to do that. Some sort of row. Insert a column here. Because it's 0 through 7, right? So I need 9 actually, because I need an extra. And then let's insert rows 2. Okay, so we have R1. And I'll put the identity one last. I don't know why I did that, but I did. So, why don't I let you guys start working out the multiplication? You have all the products there. I got the identity ones taken care of, so don't worry about those ones. And you can do this in your little groups, so divide them up or however you want to divide it up so that we can get our table filled out in an expeditious manner. It should be because it's on a square. So I think it is symmetric across a diagonal. So yeah, I don't know how you guys want to divide it up. You guys figure out how you want to divide it up. know you guys are capable of doing this. You guys obviously do need some direction. All right, your group, you're doing the first 2 rows. You guys are going to do, this group right here in front is going to do the second 2 rows. You get, oh wait, too many rows. The first row, the second row, third row, fourth row, fifth row, sixth row. You can do the 6th row, Thomas. And I'll get the 7th row. So, yeah, you guys are R1. I'll do the 7th row. And remember, R7, R1, you do the R1 first and the R7 second. Yeah, you're doing the 6th row. It should work either way. Yeah.
Yep.
Start with the one at the top, and then you do the one on the side.
Yeah. The one across.
Yeah, the one across the top. Yeah.
So, but then you write it down R1.
Yeah. So
Composition R2.
if you do RI, I'm sorry, RJ, RI, this is the top,
Yeah.
and this is the side. But you always do that.
You start with the second composition, right?
Yeah. Yeah, which? R3, okay. So starting in the first position. You guys ready? Oh, you guys are ready?
Yeah.
Okay.
So R3 is the
Next, which row did you guys have? The top one? Okay. Oh, identity.
Wait, yeah, we did R1.
Okay, so now you guys get to practice another one. Yeah, you do the last 4 of them, and you do the first 3 of them of R2.
R2.
Yeah, you guys did the same one. I didn't get that divided up right. So who has the next one figured out? Actually, we don't have to do R2 if we have all the others, because you can see Sudoku style. Yes.
Sudoku style.
Yes, we can figure it out.
Or can you do it math Doku style?
Yes, there we go.
Yeah.
We wouldn't know how to do that, though. We found that out there.
Yeah, I'm trying to, yeah.
That's just me. I don't know how to do it.
So who had row 4? Was that you guys?
I feel like this will go faster.
Who did row 5? Okay. So what is row 5? So tell me what goes in row 5. We need to do that. Square root of 9? R6? Oh, that's R3. Can't have multiple 2's in there. How about row 6? We left Thomas all alone on that one. Did anyone figure out row 4 yet? You're doing it now? Okay.
So, R4, R3, R5, R1.
Okay. R4, R3, R5. What was?
R1, R3.
Oh, there's 2 R3s in there. We'll have to fix that. Then which one?
I just said that because I
It's looking about right. Okay, I'll check this one right here. So R5, R6. 1 goes to 3, 2 goes to 4. And 2 goes to 2, which goes to 1. So this one's right here is R3. So then this one, R2, 1 goes to 3. And 3 goes to 4. And 2 goes to 4. So that one's R6. Okay. So then which one was this one? R2? Yeah, that could be R6. R2, R6. R2 was 1 to 3, 3 to 4. Yeah, 2 to 4. Yes, R7. Yeah. So then what'd we get here for R4?
I have the first 2 it's R7 and R5.
Okay. Do what? Yeah. R3, R4. Let's check that one.
So like
Four to
R5
two.
Wait, did you say R3 or
R1.
No, I was reading it backwards. It's supposed to be R4, R3. Yeah.
Okay. Sure. The next one is an R4 is R6.
Those are tied
The
together.
last one is R1.
The last one is R1.
How does it look like that?
4 is the identity. And then R5, R4. I think there's R2. I think this is R2 right here. What's R6, R4, R6? 2, 2, 4. I think it's going to be R3. Yep. Okay, so
R3,
R3.
identity, R1, R5, 4.
And which one is this one? Okay, so now if we want to look at what happens, remember we're trying to figure out what happens to the diagonals on any two pairs of these. So now we can look at the multiplication table and look and see. Suppose we were just looking at a couple of pairs. We'll just do this. And you'll see the method that you have to use to prove it. You actually have to verify them all. But that's fascinating. You would have to verify them all if you're actually writing the entire proof of it up. So let's just consider, which two do you want? Let's see, let's do R4, I don't know.
R6.
R6, okay? R4, R6, if you look on the table, R4, R6 is R3, right? Oh, I didn't mean to do that. So R4, R6 is R3. What happens to the diagonals in that case? Are they switched or are they left the same under R4? So if you just look at R4, what's happening with that one? It takes 1 to 1 and 3 to 3, but it interchanges 4 and 2, so that's a flip across the first diagonal. So that, yeah, leaves it, so note that the diagonals are unchanged under R4. And what does R6 do with them? R6 takes 1 to 2 and 2 to 1, 4 to 3 and 3 to 4, so it's a flip across the C, so that interchanges them. And diagonals are interchanged under R6. Now when you look at R3, what's happening to the diagonals under the mapping in R3? So that interchanges 1 and 1 goes to 4, 2 goes to 1. Oh, so this is a rotation. Yeah, so then that changes the diagonal too. Okay. So tell me, under the R4, R6, when we do that together, we see that the diagonals are interchanged. Now let's consider that f of R4 is going to be equal to what? F of R4 doesn't keep the diagonals? Yeah. So it's the first one that I put up there. While f of R6 interchanges the diagonals. Therefore, when you think about the composition of the two of them, the second one interchanges it, then the first ones are going to keep it without changing it. So when you do the function composition, you have the diagonals interchanged.
Are you specifying any particular things you say interchange? Or is
It takes diagonal 1 to diagonal 2 and diagonal 2 to diagonal 1. It switches, and we only have the two diagonals. If I had three diagonals, then I couldn't use that. Yeah, for this problem. So we can, therefore, in this case, f of R4 composed of R6 is equal to f of R4 composed of f of R6. That makes sense? We have done this verification when we talked about isomorphisms a little bit. We would actually need to, if we were writing this up in the proof, we would need to verify all of them. But what people do, instead of actually going through and typing up the verification of all of them, we just say, similarly, we see that by inspection of the table, f of Rj composed of Ri is equal to f of Rj composed of f of Ri. Now, in fact, you actually have gone through that process. When you type that out, you should have gone through that process. We're not actually going to go through the process and verify all 64 possibilities on there, but that is what you would do. Yeah. That, you have a problem similar to that, but I think you only have like 4 operations or something like that, so it's not nearly as difficult. Here again, I don't want you to type up all the properties for it. Just verify in scratch paper and show me one of your verifications. Give me the table, etc. Kind of like what we've done. I believe that's on this homework assignment. Okay. Let me get back to the right page here. And that's kind of like your number 4. Notice one thing I haven't done yet on this. Don't forget that you have to do this part. And that is, what is a kernel? Yeah. Everything that F maps to the identity. So we have to figure out what this is going to be equal to. What all gets mapped to the identity? Well, under F, what is the identity? Diagonal 1 goes to diagonal 1, diagonal 2 goes to diagonal 2. That's our identity mapping. So which of those elements on page 73 got mapped to the identity? Obviously, the identity operation gets mapped to the identity because the identity didn't change anything to begin with. Oh, that didn't work.
Wait, doesn't R6 flip on?
1 goes to 2, 2 goes to 1. Yeah, it interchanges it across. Yeah. That looks good to me. Everything that gets, whose diagonals are unchanged. Those things that don't flip the diagonal. So that is a kernel. Your first problem is going to ask you to show that it is a homomorphism, and you do it by making a little multiplication table. I believe you only have 2 or 3 little elements in your table, so there's not much for you to verify. What? It's not quite the same. Notice what it says about it.
I mean,
You imagine a square as a piece of paper lying on a table, and you have side A facing you and side B facing away from you. And you're going to do a motion on the square, and all you care about is which side is up.
right. But wouldn't it have the same, isn't it laid out? the
Yeah.
same
You're
problem,
starting
just-
as D4, going to S2. Yeah. So it's going to be very similar to this one. When I say you only have a couple of operations, your second thing that you're going to, yeah,
Okay,
Uh-huh.
yeah.
is not that much. So it's very similar to the one that we just did here. You're starting with your dihedral group D4. Okay, any questions on that? Any other questions on that? Yeah.
I think it, what do you find that group that sexuals are
Okay.
5 or 2 are?
Yeah, that's the
Why are they-
dihedral group D4. And it's all the symmetries on a square.
All the symmetries on the
Yeah, so you can rotate your square, and you can flip it across diagonals. And
That's
so,
not based on 2, like, because like R2 maps to R2, R2.
oh, that all comes from what gets mapped to each other comes from what each of the permutations was meant to be so R1 is on page 73, and it lists what each of the vertices of your square get mapped to. On page 73. So that's what each of those elements are. Okay? And then your R1 composed of R3, that is, you do R3 first, it's like your function composition with your 2 permutations like we've done before.
So when 2 of them come together.
Yeah, so you'd have your first one and then your second one. You remember how to do that?
Yeah, well, go back to, what was your answer again?
Oh, for the kernel?
Yeah, the kernel.
Oh, the kernel is just whatever has, under those operations, R1, R2, R3, R4, up to R7, which ones leave the diagonal unchanged? So if you go and look at, let's see, I got to go back to that page now. Suppose you're looking at R1. R1, if you look at the picture, R1 takes 1 to 2, takes 2 to 3, it takes 3 to 4, and it takes 4 to 1. So that's a rotation. When you rotate your square, what's happening to diagonal 1? Is it staying where it is, diagonal 1? Or is it getting moved to diagonal 2? Think about your
Right.
rotation. A goes to B.
How much you rotating by?
Well, you can tell it's by 90 degrees because A is going to B, B is going to C, C goes to D, and D goes to A. So you spun it by 90 degrees. So that A, the first diagonal, ends up being on diagonal 2. So that one is not one of our identity mappings. But if you went A to B and then B to C, that took diagonal 1 back to itself. Because when you go from A to B, that takes diagonal 1 to diagonal 2. And then when you take B to C, it's taking diagonal back to itself. Because 1 goes to 2 and then it goes back to itself on 1. And so you're checking to see which of these operations are 1, or 2, or 3, or 4, or 5, or 6, or 7, or the identity. Leave the diagonals where they are.
Okay, I got it.
Okay? That makes sense? Did that answer your question?
Yeah.
Kind of, yeah? Okay, are we ready to go on, or did we have more questions on that? The kernel is what is unchanged, what is mapped to the identity. In other words, what is your identity function? Everything that gets mapped to that identity is your kernel. And in different things, it's going to be different. Like under the integers, is what gets mapped to 0. You know, that type of thing.
So, on R2, you're saying, I'm trying to figure out how you, like, what are you looking for when you're finding a graph?
I want to know, F has two mappings. It takes the diagonal 1 to itself and diagonal 2 to itself. That's the identity mapping for F. And the other mapping is take diagonal 1 to diagonal 2 and take diagonal 2 to diagonal 1. So I'm looking to find out which ones of these. Here is our identity under F, and then the other. So which ones have this operation on the diagonals? Of all of these, R1 to
And just these
R7,
two diagonals because of all.
for just those two diagonals. So if you were looking at, tell me about the behavior of R3 on that page.
270 degree
Rotation. Does that leave the diagonals the same? Yeah, because it takes it to B, then back to itself. And I think it changes it. 270 should interchange it. Because if you think about it, 1 goes to 4, so that means the diagonal, this should go 1 here. So if this point is mapped down here going all the way around to this point, then this point on this diagonal ends up being mapped onto that point on the other diagonal.
These diagonals are changed.
So the diagonals are changed. So our 3 wouldn't be in our kernel.
But now
Our 2 takes 1 to 3. So that means this one is mapped back to here. So yeah, it flips it end for end, but the diagonal stays on top of itself. Yeah, that makes sense? Okay. On B2, that's one of your homework problems in chapter 14. I'm going to let you start working on it right now, and then we'll talk about it. But it says show that this is a homomorphism, and it's for derivatives, so it should be something relatively straightforward. Then we'll look at C8. Let me wander through and check your outlines while you're working on that. Okay, so how would you prove this one? I'm not going to type it all up because we're almost out of time.
Wait, it's not what you just showed us?
Yeah, it is.
Oh.
Actually, let me just, you guys can type this one up. Let's look at this last one together because we are going to be out of time, and this one's a fascinating one. It says let G, H, and K be groups. Prove that the function f that takes G to G defined by f of x equals to x squared is a homomorphism if and only if G is a billion. So we don't need to know anything about H and K in this problem. So we'll take that out. So let's get the hypothesis. Let G be a group. It's if and only if. So what do we want to show first? Which direction do we want to go first? What does that tell us if it's a homomorphism? Yeah, for all A and B and G, we have f of A equals to A squared, and f of B equals to B squared, and let me look how that goes halfway at the bottom of the page. Better? And f of AB has to be equal to what? Yeah. Yeah, so what you're going to have, f of AB, let's calculate this. This is AB quantity squared, but f of A was equal to A squared, and f of B is equal to B squared. So put that all together, and you're going to have f of AB has to be equal to AB squared has to also be equal to A squared B squared, because it's a homomorphism. You guys see that? Just putting them all together. But what do we know? If I do AB squared, that's equal to AB, right? So that tells us that AB has to be equal to A squared B squared. But then what does that tell us? If I do left inverses on A, we get BAB is equal to AB squared, right? And if we do right inverses on B, we get BA is equal to AB. Oh, what did that tell us about our group G? Yeah, G is a billion. Yeah. Now go the other direction. So assume that G is a billion, and we want to show that F is a homomorphism. So we're going to let A and B be elements of G. Then since G is a billion, I know AB equals to BA. So what does that tell us about A squared B squared? Yeah, except I want to interchange it a little bit. This is AA times BB, right? So AB, which is AB squared. Okay? So combine that with what F is equal to, and you have F of AB, which is equal to AB squared right here, has to equal to which is F of A, F of B.
Wait,
It went by pretty fast, didn't it?
no, I was just like, oh, I see. I saw it. I just
Yeah. And F is a homomorphism.
actually right.
Yeah, because you're just trying to get F of AB equals to F of A times F
Or is
of
that
B.
your it's not that baby, so I was like,
No.
I forgot that.
Yeah, it's just square. Okay, I didn't make it pretty, but that essentially gets it across to you. Kernel is everything that's mapped to the identity. What is the identity function? F of x equal to x.
Yeah.
Oh, wait. Under addition. Yeah. It's all your constant functions. Yeah, all your constant functions are the kernel. Yep. Question?
Can you scroll up to, okay, wait, I guess keep scrolling up. We said it was a,
Yeah, you assume it's a homomorphism first.
all that gives